Welcome to The Explainer. Today we're going to talk about some really strange but incredibly powerful math. It's the stuff that secretly secures a huge part of our digital lives, everything from our messages to our money. It's called elliptic curve cryptography.
Right? This is the exact question we're going to answer today. I mean, it sounds a little nuts, doesn't it? But it's actually one of the most elegant and powerful ideas in modern security.
Okay, so let's get right into it. To really get why we need this new kind of encryption, we first have to talk about the problem with the older stuff.
So, for a long time, systems like RSA were the undisputed champs of security. They're strong, no doubt, but they're also, well, they're bulky. They need really, really long keys to stay secure. And those long keys, they're slow and they gobble up processing power. Now, that's fine for a big desktop computer, but think about the world we live in now. It's all smartphones and tiny chips in our credit cards. We needed something just as strong, but way leaner and faster. And so, cryptographers turned to this kind of weird-looking mathematical object, something that mathematicians had been studying for centuries, not for security, but just because it was beautiful and interesting. They turned to the elliptic curve.
So, have a look here. On the left, you've got a circle. Nice and simple. You probably remember the equation from high school. It's predictable, it's symmetrical. On the right, that's an elliptic curve. And first things first, despite the name, it is not an ellipse. It looks a lot stranger, but as we're about to find out, it has some very, very special properties that make it perfect for cryptography.
And this is the blueprint for all of them. It might look simple, but just by changing those A and B values, you can create a whole universe of different curves, each with its own unique shape, kind of like the ones we just saw.
Now, there is one critical rule that every single one of these curves has to follow. This formula you see here, it can't equal 0. And all that rule does is make sure the curve is smooth. No sharp points, no places where it crosses over itself. And that smoothness is absolutely essential for the weird math we're about to perform on it.
Okay, this is where the magic really starts. We're going to completely throw out the normal rules of addition. We're going to define a brand new way to add things together that only works for points on our curve. It might sound complicated, but it's really just a little geometric game. You pick 2 points, P and Q, you draw a straight line through them, you see where that line hits the curve a third time, and then you just flip that third point vertically across the horizontal axis. That final spot you land on, that's what we call P plus Q. And here it is, you can see the whole thing in action. Look, the line goes through P and Q, it hits the curve again way up top, and then it reflects straight down to our final result, R. And here's the amazing part. No matter which 2 points you start with, this little trick always lands you on another unique point that is also on the curve. You can't escape the curve.
So, how does this quirky little addition game become the foundation for rock-solid encryption? Well, it's all about creating a kind of mathematical one-way street, a trapdoor.
So imagine you start at 1 point. Let's call it P. Now you add P to itself using our new rule. That gives you a new point, 2P. Okay, now let's add P to that point. You get 3P. What if we do this over and over and over again, say a secret number of times? Let's call that secret number D. You're basically hopping along the curve from point to point, and you eventually land on a final point, Q.
And here is the core of it all. This is the whole secret. For a computer, doing that multiplication is super fast and easy. If I give it the starting point P and tell it to hop, say, 50 million times, it can find the final point Q in a snap. But, and this is the crucial part, if I only give you the starting point P and the ending point Q, you have no way of figuring out how many hops it took to get there. It's impossible to work backwards. It's a one-way function, a trapdoor, easy to fall through and possible to climb back out of.
And check this out, because this is what it looks like in the real world. In actual cryptography, we don't use a smooth line. We use something that turns the curve into a scattered mess of individual points, kind of like a cloud. So now, if I give you a starting point P and an ending point Q in this mess, can you figure out the path of hops between them? No way! Good luck! It's practically impossible. And that impossibility is what gives us security.
So why does any of this abstract math actually matter? Well, this elegant one-way function isn't just a fun brain teaser. It's the engine that powers a huge chunk of our modern digital security.
Seriously, this math is working behind the scenes all the time. When you get a software update, it's digital signatures using this math that prove it's the real deal. When you send a message on a secure app or do some online banking, it's used to create the secure connection. And, of course, it's used to actually encrypt your data, keeping it safe from anybody who might be snooping.
And this chart right here shows you why it completely took over. Because its trapdoor problem is so uniquely difficult, ECC gives you the same level of security as older systems, but with way smaller keys. I mean, look at that. A 256-bit ECC key is just as strong as a 3072-bit RSA key. That's a massive difference in efficiency, and it's what makes it absolutely perfect for all the small, battery-powered devices we all use every single day. So really, the main thing to take away is this. In a world that needs security to be both super strong and super fast, elliptic curve cryptography gives you more security bang for your buck. It's this elegant, difficult math that lets our tiny little devices pack such a powerful punch. It really makes you wonder, right? What other beautiful secrets are hidden away in the world of numbers, just waiting to solve the problems of tomorrow?